Good morning, everyone. I'm Vanbaelen from Steding DSO, and I will be your moderator today on behalf of Flexible Power Alliance Network and SmartN. I welcome you to the 5th webinar of FLEXCON 2020 on new concepts in energy networks. We will have 4 presentations today, and during the presentations, you can interact with us using the question pane from the GoToWebinar. Please do that so we can have a lively discussion after the presentations that take place. Also good to know that slides and recordings of the presentations will be shared afterwards. So you will receive information from that. They will be shared on the FLEXCON 2020 webpage, and not only from this webinar, but also from the previous 4 webinars on electric mobility, devices and flexibility, markets and industry and commercial aspects of flexibility. And so today we are going to see how this all comes together in new concepts in energy networks. And let's first see who is attending the meeting today. So Adrian, can you share the poll for that? Okay, who are you? And please select one of the options. My focus is aggregators and markets, or my focus is energy generation, distribution. My focus is smart technology. My focus is e-mobility, or something else. Please let us know. Okay, we're back now, and I think, well, a lot of aggregators and markets today, together with the focus on smart technology. Not yet any e-mobility and vehicle to grid. Well, quite a mixed audience, except for the last one. So let's see, and I will now introduce you to the presentations we have today. The first one is on flexibility and the Internet of Energy. The second one on local energy communities. Then we go to hybrid renewable power plants, and the last one on investment plans for grid and infra. So all together, we will see new concepts on both technology, the market side, generation, and grid planning tools. And I'm happy to introduce you to the first 2 speakers from Elia and ENGIE. And they are Pieter Vanbaelen and Guillaume Chicco. Pieter joined Elia in 2015 and works as a project manager within the team of future market development. He specialized in demand response and decentralized flexibility, and his focus today lies on the innovations that are taking place on the residential level. Guillaume, he joined ENGIE in 2018 and works as a business developer within the team that develops products and services for residential customers. Also, his focus is on innovations that are taking place at the residential level to enable an active role for the customer of the future. Pieter and Guillaume, please take it away.
Thank you. Good afternoon, everybody. Today I will talk about Flexity, which is a collaboration pilot project in which Chicco, ENGIE, Voltalis, Jetlix, Fluvius, CGI, and Elia investigate residential flexibility in Belgium. So to start off with, first some context as an introduction. The transition of the electricity system is one of the major challenges of the century. The switch towards a decarbonized society brings fundamental challenges for the electricity system. And as Flexity, we truly believe that the end consumer will play a central pivoting role to make this happen. Digitalization will be the catalyst that makes a link between the energy transition and the end consumer, enabling, in fact, this end consumer to lower its energy bill, to actively participate in the system, while maintaining his comfort and benefiting from the technological investments that he made, such as you bought an electric vehicle, solar panels, or heat pumps. Next slide. Well, to make this happen, this will require a shift in paradigm. As we see today, the center of the system is largely focused around centralized generation, with limited digitalization and communication at lower voltage levels. There, tomorrow at the right side of the slide, we see that more variable and new renewable distributed energy sources will need to be managed properly. And in order to do so, we as Flexity believe that residential flexibility will play an important contributor to help safely manage the grid of tomorrow. Now, on this next slide, we see Flexity was born out of an intensive 5-day workshop that was part of the so-called ENGIE ecosystem. Now, what is it? Well, it's an initiative of the Belgian grid operators to unite all market parties to develop new ideas. So basically what we do is we put all the market parties, a lot of them, in the same room. We had 5-day workshops, brainstorming, intensive workshops, and out of these workshops, Flexity was born. Now, what do we concretely do? Flexity objectives are basically twofold. First, we want to test which household assets can technically be operated, and if so, what is the value that we can generate for the end consumer. Important to mention, we leave the existing commercial communication setups untouched. So what does it mean is, let's say that you have an electrical vehicle that is connected via the manufacturer's backend, and we try to reuse this communication setup to safely operate the electrical vehicle. And of course, we want to operate these household assets without loss in any comfort for the end consumer. This is the first objective. Second objective was to test if we can build reliable data streams and enable basically that a safe settlement mechanism for the settlement of our balancing and wholesale markets. Now, Guillaume will go further and give us a more deep dive view on what did we learn in the pilot project.
Sorry, thank you, Pieter. So before jumping into the takeaway and what we have discovered in during the pilot, we want to highlight, and we will show a video whilst I'm explaining what the team have put as a setup behind the scene for each objective that Pieter explained. So to steer the different assets, we have installed Chicco technology to steer accumulative heating mainly around 15 households, which is the video that is shown. We have also operated a pool of EV around 20 to test, and we will come back in the result, different value pool. Voltalis has also operated 4 heat pumps to test load reduction so that they can be the load reduction can be sold in the wholesale market. So this is to support the first objective of steering the asset and bringing value to the end consumer. For the second objective, CGI, Elia and Fluvius worked together to collect the access point household consumption from the digital meter of Fluvius throughout the gateway in order to correlate and see if some metering data of this flexibility are reliable and can be trusted to valorize this flexibility. So before starting, we would like to introduce a pool, and we start from a customer perspective. In order that the customer open their doors for a service and bring value, we wanted to know a bit what's the main reason to participate in such a pilot. So we are curious to have your point of view. So Adria, if you show the pool, let's see from the audience what will be your main driver if you had been contacted to take part of this pilot. Okay, I have. I cannot see the. I cannot see the result of the pool. So, can someone can tell me when?
Guillaume, I want to give the audience still 15
yeah, no, but the thing is, I'm a bit blind on. Yeah, we can wait. I just don't see the results or can comment on the pool. I don't know why on my computer. I don't know if it's an issue.
Jan, shall I share the
results? Sorry, again, I will share the results. Pieter, also they were also for you. So the results are on participation in energy transition got highest ranking. Almost half of the people see there the pilot they participate taking place, and on second place, both energy saving at home and discover new technology, both about 20%.
Okay, thanks for sharing the results. So now we can start sharing from what we have learned, and it's quite interesting to see there is quite a change or a shift from people participating in maybe that we are more involved than our the more normal or general standard consumer. But what we have seen from the main motivation is that is really around potential saving they can get and less around the sustainability of an electricity system, and also the high interest into technology, so more early adopter and technology savvy person. But we will come to that in the result. What we have also checked and gathered from the consumer is that from a technical point of view, we successfully steer the different assets throughout different technology for EV, heat pump, and accumulative heating. But we have succeeded not to impact their comfort during this activation, and they have confirmed this to 100%. The last point we also wanted to underline, which we know is a common issue for this type of new technology, is the privacy issue. So we have implemented and follows the GDPR guidelines, and we have asked if the customer felt unease of the data he has to share of his consumption, and he was confident that it was handled correctly, and also didn't see this as a barrier because the service we were providing was removing the barrier and making him willing to share the data to have this service. So if we then focus on the result during the pilot, we can categorize them in 6 main topics. So starting from the right, there will be a focus on how did we steer the different assets and what are the technology we could use. Then we'll come back to the main driver and how to shape a future service. We will look at what are the different value streams to valorize the flexibility. And then starting from the left, which is from a more technical point of view, what are the compliancy and issue we may have in terms of data exchange to enable this service? What did we find out on the prototype of the dongle to gather the access point household consumption, and the cross-check mechanism that has been tested? So if we then on the first 3, if we deep dive, the way we enable this flexibility are mainly 2 approach. The first one we have seen on the movie require a new infrastructure or gateway hardware in the house that needs to be installed, which is such as a Chicco technology. and there is another way which was used for the EV fleet, for example, which is based on an OEM connectivity device, such as the car that has some connectivity, for which we are using to steer the assets. In terms of the driver of the consumer, we saw that the high interest is a bit different of the people listening on the call, but it's mainly the savings, and sustainability is not a key action to join this. But indeed, we had a limited number of consumers, and we need to validate these findings to a larger audience, which will be one of our next steps. We also check the willingness to pay for such a service, and people are open if this, under the condition, I will say that the investment they are making is kind of payback in a rather short period of time. So in terms of the value for the value stream this service and product can bring, we can summarize them in three folds. The first one is the day and night price, so trying to shift for the customer in an automatic manner his consumption at a cheaper time during, so mainly at night. But there will be also dynamic pricing that could play a role in the future. The second is the wholesale price, to try to optimize the day ahead and the sourcing of the energy. And the third one is all around the balancing services, such as an ancillary service such as IFRA. So for EV, what we have seen is that EV can play a good role in all these three value streams. However, for accumulative heating, what we have found out is the main driver will be the balancing services, such as IFRA. We know accumulative heating exclusively consume at night, so the first value pool to shift at a cheaper time doesn't really apply. And the volatility is also of the market price is rather low at night, so the wholesale pricing is limited. For heat pump, we tried the strategy to reduce without impacting the comfort, the load of the consumption, so that we can sell this reduction in the wholesale price. If then we focus on the more technical takeaways, enabling such a flexibility rely on, I will say, three main requirements. The first one is compliancy with the measure of the device to have the right granularity and precision. So out of the two approach, having a new infrastructure or hardware install is the easiest and work perfectly to meet this requirement, where there are still some issues to iron out when you rely on an existing connectivity OEM setup, which was the second approach. The second requirement is the fact that the data should be collected locally and routed directly to IFR platform or IOE energy platform. This is still a blocking point that are being discussed on how we could resolve this, because during this pilot, the data was routed centrally throughout the backend of a technical service provider. The last element is a real-time collection of assets, which was made possible during the pilot to ensure the data is shared in real time throughout the different parties. On the dongle and the prototype, we wanted to test two aspects based on the Fluvius digital meter. So this meter allowed to have P1 data and S1 data, which is the raw data of the meter, which require high amount of data. So we didn't succeed of having the right setup to collect the S1 data onto a platform. We will have need a much more robust hardware, and what we with the team feel is that having such a hardware will prevent to have a positive or economical business case. So we will be basing on P1 data, which was then successfully shared and collected, and there are still work to be done to ensure the availability in and good quality throughout the period to ensure the guarantee of this feed and stream. The last point we did, supporting by CGI, was the cross-check methodology to measure and rely on sub-metering to see if the sub-metering can be trusted by cross-checking the P1 data from the smart meter trusted access point. And we have a good feeling and some reasonable insight that on probabilistic that we can do this cross-check with correlation to open up the residential flex based on this mechanism. I will leave the floor for Pieter to conclude on the pilot and the next steps.
Yeah, I will make it short. So way forward, what lies ahead for us? I think in general, all project partners were very enthusiastic and they are positive to scale towards a wider demonstration phase. But therefore, we must tackle one of the largest barriers that we face is that communication requirements for participation in the balancing market. So therefore, in the next step, we will see how data exchange requirements on low voltage level need to evolve to enable that this residential flexibility can officially participate in our products. And then secondly, also taking into account upcoming evolutions towards a capacity tariff in the northern part of Belgium as from 2022, we will see how Flexity, how this capacity tariff will impact our current optimization strategies, how we'll need to adapt so that we can avoid peak consumption on access point and hence offer the end consumer an optimized energy bill in the end of the month. So that was it. Thank you for the interest. Give the word to you, Jan.
Yes, thank you, Pieter and Guillaume, for sharing your insights on a very practical example on implementing Internet of Energy. Good to see that. And we have some questions from the audience. So please stay online. And here's the first one. Could you be more specific on the financial results? Or in other words, what are the financial results for the consumer and for the DSO involved?
So first of all, I think that we need to make a separation between the different household appliances that were operated. So if you take a look at, for instance, electrical vehicles, there we saw that yeah, an important part came from the optimization of day-night. And when you look, for instance, at the optimization of day-night, then I think almost 60 or 70% of the earnings that we can generate comes from lowering the distribution costs that needs to be paid by the end consumer. So I think definitely on this distribution grid cost, which is an important element on the energy bill, if we can optimize there's a huge value to be made. And then participation in the FR market, we see quite a big potential there, but there are it's merely estimates that we're doing there because it was a technical pilot for AFR. We didn't officially participate into the system, so there we need to take a look where what will be the actual revenues that can be generated once really participating into the system. And then for heat pumps and electrical boilers.
Yeah. So as I understand, well, it will also be part of the next steps to get further insight into that.
Yeah.
Okay, thank you. We have another question. Yeah, we have another question. Did you trial DSO congestion management as part of your platform? And if not, are you planning to do that in the future?
That was part of the initial brainstorm, but no, DSO congestion management was not taken into account, so we didn't take any locational parameters into account when activating flexibility. This will definitely be a point to tackle in future, but I think that the scope, it was already quite a big project, so it was in the end it was put out of scope, and we mainly focused on optimization function wholesale prices in function of day-night and balancing, so congestion was out of scope.
Okay, thank you, but coming up for one of the next phases.
Yeah, definitely.
Yeah. Okay, another question. Are you also welcoming new partners to join the project to provide technology and flexibility?
There, I think I will answer not as part of Flexity, but I can answer as part of the IO energy ecosystem. I also need to take a look internally, but the IO energy ecosystem, there will be a second version where we again will be organizing brainstorm sessions with other market parties to see if we can develop new concepts, if we can put up new pilot projects. So, and the second version of the IO ecosystem will be launched somewhere in the end of 2020, beginning of 21. But I can definitely, if you can contact me bilaterally if you're interested, and I can put you in contact with the right persons of the ecosystem.
Okay, thank you for that. I heard about collecting the data was quite a challenge. Can you elaborate a bit more on what the most important challenge was regarding the collection of useful and reliable P1 data?
It's a very good question. So when I purely look at the aspect of collecting the data, so we have everything installed, which was also quite a big hassle. Once we had everything installed and we were collecting data, I think connectivity issues. Evidently, it was an important aspect. For instance, also due to saturated 4G networks, which were at a certain moment also related to the Corona crisis. The fact that digital meters are installed typically in the basement where you have poor 4G network, which makes it difficult to collect the data and stream it on a 1-second basis. So it was mainly due to connectivity issues, but when we were lowering the granularity, so initially we were at 1 second, and when we lowered the granularity to 4 seconds or to 10 seconds, then you saw also an increase in availability because we needed to use less of the bandwidth available. I hope this answers the question.
Yes, I think so. I think
one additional, there is also the process where the customer has to also accept to share his smart meter data, which were also one of the synchronization between the installation and the consumer accepting to share this data was also kind of adding difficulty to ensure that everything was into good place to share it, I think, as an initial setup.
Okay, thank you for this addition.
Yeah, I think we absolutely agree there. It was,
we can do one last question. It's about the business case in relation to operational and maintenance costs. And how do you think that those operational and maintenance costs will be in comparison with expected flex income and savings? Do you have any idea on that already?
So if I try to answer, I think we mentioned two approaches. So we have, if we look at scaling it up, the approach of installing hardware put more constraint on on the setup and the maintenance rather than relying on an existing connectivity approach. But we have to balancing out with the fact that enabling this service with a hardware that you control or that you have installed could be easier to ensure the quality of service, or could be or so far the requirements that are put in place. So I think as next step we will have to see and have a larger pool to really see where the best balancing and pros and cons of each, to see how we can enable it in a positive case for the customer and the partners.
All right, thank you.
Maybe one last point to conclude on. Yes, I think also the business case, what we saw and I find very interesting, is that business cases really rely on the fact that all value streams are open. So the fact that you cannot solely build a business case basically on day-night optimization. We need to make sure that also our balancing products are open, and that we enable market parties to be able to stack value across different value streams. And that is exactly also what we want to do in the next phase, is to make sure that all the market segments are open, that also our balancing products are open for participation, so that market parties can truly stack value across different value streams. And only in that case, I think that it will be a major contributor to building and boosting the development of residential flexibility in Belgium.
Okay, thank you for this last point, which I agree will be very important to open up the real business case for these kind of propositions. Well, thank you once again for your presentation and answering the questions. And we will go to the next topic. It is about local energy communities in practice by Mihaylov from iLeco. Well, Mike is a blockchain architect at iLeco. Welcome, Mike. Working in the domain of smart grids, renewable energy, and blockchain technology. He is the product owner of iLeco's local energy community dashboard tool, and in addition is currently managing several teams in the fund that in projects iLeco is running. He's got a background in artificial intelligence and several degrees, including a PhD on that topic. Please, Mike, introduce us in the world of local energy communities.
Thank you, Jan. So iLeco is a software enabler for local energy communities, and we have an advanced energy management software that handles the full chain from measurement of devices through forecasting, simulation, optimization, all the way down controlling those devices. Our vision is for a fully sustainable energy society, and we believe the layered energy system is key to achieve that vision. The LES concept is originally started by ENGIE21 and Stedin. iLeco participated early on in the design decisions as well. Before we go further, I want to get a bit of a feel of the audience. We had a similar question earlier, but if you could, Adrian, start the poll. So yeah, what is your level of involvement in local energy communities? Do you have just general knowledge and you're eager to learn more? Do you have actual plans to develop solutions and you're looking for partners? We got one question in the previous talk. Did you recently start developing solutions, or are you already piloting solutions for local energy communities? Cast your votes now. Very well, and once we see the results, I can proceed. Very well, so mostly it's general knowledge, but we already have some companies or consortia that are running pilots in local energy communities. Thank you very much for your votes. We believe the layered energy system is a future compatible support mechanism that enables local energy trade. And when I say that, I don't mean peer-to-peer energy trade where neighbors are competing with each other. Here we mean peer-to-community, where you buy energy from the community and you sell to the community. So all sellers, for example, get the same price. It's dynamic price over the day, though. But this local energy trade lowers the electricity bill of residents because local energy is cheaper than external energy. It increases the community self-sustainability. More of the local energy stays local. Reduces congestion and therefore grid investments because there is a flexibility component built in the concept. And with that flexibility component, this also amplifies the value of solar and flex. This, in a way, strengthens the investment case for batteries, for example, bring more value. So in short, for consumers, they buy local energy cheaper than external energy because you don't have to pay transmission fees, for example. And for producers, you sell your local energy to the community and you earn better than a feed-in tariff or net metering, which is in fact being phased out in some countries. So I will show you here a high-level video in order to see how the layered energy system works overall, what is its role in local energy communities, and what iLeco and Stedin are doing. So I will start the video, and then I will continue with the presentation.
Nowadays, we increasingly generate our own energy by using sustainable energy sources such as solar panels. Unfortunately, solar panels cannot be installed on every house, leaving some people sidelined from cooperation towards a better environment. What if, by working together, we could set up our own local energy communities and start using energy that is generated locally for local purposes? With the solutions of iLeco, this becomes reality. Energy supply and demand are monitored continuously for each participating house in the community. A house with solar panels has a clearly lower energy demand, especially during the hours with the most sunlight. A house without solar panels has a constantly higher demand for energy. By working together, it becomes possible for houses that produce redundant energy to share it with houses without their own energy production. Market supply and demand are constantly weighed over and over again until a deal is reached. When the capacity of the energy network is exceeded, this is noticed thanks to continuous measurements performed by Stedin. iLeco responds automatically by sharing and reshaping energy within the community, which causes a general reduction in central energy demand and prevents extreme spikes. Not only does this improve the local cohesion between the inhabitants of the community, it also makes a considerable difference on the energy bill. By multiplying this system of local energy communities on a large scale, every citizen can contribute to a world with more local, sustainable, and affordable energy. Do you want to cooperate with your neighbors by creating a local energy community? Do you want to lower your energy bill? Check out our white paper on layered energy systems at iLeco.energy.
Very well, I will continue with the presentation. Right. So what are these layers of the layered energy system? On the first, so first of all, here you see the white paper, and you can download it also from iLeco.energy. So on the first layer, a local energy community behind a given transformer trades energy locally on the local market. So that's the first layer. Then any deficit or surplus is traded across communities or to other local markets. And the third layer, energy is bought or sold from the wholesale market, which is more expensive because then you have to pay the transmission fees. Stedin constantly monitors for grid safety, and TenneT is ordering balancing, for example. So this is the three layers of the layered energy system. And before we proceed further, here is the second survey question. Adrian, please launch it. And we had a similar question actually when the previous talk with Flexity. if you would have the opportunity to join a local energy community initiative, what would be your top driver? So let's see whether the answers are consistent with the previous survey. So here you have several options. Are you interested in lowering your electricity bill, or having community self-sustainability, so more of the local energy stays local? Do you want to help grid congestion and improve the system reliability because of the penetration of renewables? Do you want to participate in the energy transition, or help combat climate change? So what would be your top driver? Lowering the electricity bill, I see, is the top driver. Interesting results, considering the previous poll had also participated in the energy transition as the major driver. But I see these answers are in line with the survey questions we've asked also residents. So maybe we can now switch back to the presentation, and I can show you. So we asked a similar question to the 2 pilot locations that we deployed to the LED energy system in the Netherlands. In Hoogdalem, their main driver was self-sustainability, but these were more middle-class houses, while in Woerden, the main driver was economic, and these were social houses. I also want to point out that these 2 pilot locations will be used in the just started European project Energy to Peers, which iLeco is a partner of, and where we're going to deploy an enhanced version of the layered energy system. But going further into the details of LES, what is it comprised by? So what is it built? It is a set of software modules that can be run by individual parties, like companies, DSOs, or energy cooperatives. So these are individual apps, and the basic 3 apps that make the whole concept possible are the market, also called market service app, which matches buy and sell offers on the 3 layers of the market. Also, grid safety app monitors for congestions and opens flexibility rounds. And the third component is the local energy community dashboard. Also, we call it prosumer app, which is the residents' single interface with the LES ecosystem. And this is one of our main products at iLeco, the prosumer app in LES. This is the only application with a user interface. The other applications are services that are running without the user interface. And what the communication between these apps happens through the blockchain and a set of smart contracts these facilitate the information exchange between the different apps without API. So you can see there are no direct connections between the different apps. But also we use the blockchain as a trustless information storage. So instead of entrusting a single entity, a single party with keeping the whole database, we keep it in the blockchain, because then we have the no lock-in effect. So any party, in fact, is replaceable by any other party. And that was a design decision of LES. In our case, we are running the Energy Web Foundation blockchain, but any blockchain with support of smart contracts would work as well. And an interesting fact is we're working on open sourcing these apps so that they can be deployed, so that any community can download this set of apps and deploy it on their premises and explore the layered energy system concept by themselves. And of course, we are always happy to provide the prosumer app interface for those communities. But what does a day look like in the life of a Woerden resident? You're probably asking. There are several steps that happen on a daily basis, and those are repeated each day. This is, of course, valid for other communities as well. So first, iLeco computes the optimal energy bits for the next day using our smart forecasting algorithms. And the user can review those bits for the next day. They can also modify those bits or not if they choose so. So they don't have to take an action, but they can if they want. Then the prosumer app publishes those bits to the blockchain, and those bits are then fetched from the blockchain by the market app, which then matches the bits with other residents and across communities and with the wholesale market. So the 3 layers. The grid safety app then checks the market next day for congestion and opens flexibility bidding rounds if there would be congestion, like you saw in the video, for example. The prosumer app, so iLeco, then computes the optimal flexibility potential of each house and offers these as flex offers on the market. The grid safety app accepts or rejects those offers, and then the market program is updated to reach a final program for the next day. That program is put on the blockchain and fetched by iLeco, which then we display on the dashboard for the end user. But the process doesn't end there. Next day, when the next day comes, iLeco then steers the flex resources of each house in order to minimize the imbalances for the end users. So that's where smart steering is employed. Very well. As a summary, iLeco offers the local energy community dashboard, or a prosumer app, which is the resident's interface to the LES ecosystem. But it's more than the interface. It's an advanced optimization software that, for example, gives insights into the energy usage. For example, you use more than typical right now. And also, we provide actionable tips when you should use energy so that you use more of the local energy and therefore lower your bill. We also incentivize user participation using gamification elements. So people can earn points and badges if they help the community, if they use a lot of green energy, and so on. So this motivates user participation. We also facilitate energy trade using automated trading agents that optimally determine the best price for every resident, given their preferences and price sensitivity. And we, of course, employ smart steering of flex assets. So that's about it. You are welcome to schedule a live demo so that you can see the local energy community dashboard in action. And if you like to do so, contact us via iLeco.energy. Thank you very much. Jan, back to you.
Yes, Mike, thank you for this interesting presentation on the local part of the energy system. New steps in that. In some real life pilots. We have some questions from the audience. Here's the first one. How do you see that local energy communities using the layered energy system will conflict or compete with energy suppliers' offerings?
They can work alongside. We have a similar case in a new pilot. In ENGIE in particular, where this concept will be integrated as part of an energy supplier. So this is a new offering or business model of energy suppliers. In fact, is to offer this concept. This concept doesn't work by itself, out in the open. It needs to be adopted by market agents, market actors. So it works and it's very compatible with energy suppliers. Of course, the regulation is one barrier that needs to be considered. And that's why we're running these pilots, in order to make a good case for adapting the policy to be more favorable towards such concepts.
Okay, could you maybe say a little bit more on the role of energy retailer or supplier in the ecosystem that you showed us?
Yeah, they can. So right now, maybe I hear my voice twice. Maybe mute yourself.
Mike, maybe you can mute your other computer.
It is muted. It is muted. Yeah. Well, now I don't hear. Yeah. So energy suppliers can offer this as part of their services. This is what we are doing already in another pilot. And your question was, what are the benefits? So the idea is that residents need to choose their energy provider. And when one provider offers such an innovative solution that brings more value than the traditional net metering, for example, then I would say it's an obvious choice and therefore a favorable business model for that energy supplier. I don't know if that answers your question. Jan, you're muted.
Yes, you asked me mute, so I was muted. Once again, I think it's bridged to the next question from the audience. You use an argument for cheaper energy that you don't have to pay transmission fees, but it's stated here cost will stay. So I'm not convinced that your argumentation will hold on the longer term if this concept would be largely deployed. Therefore, very interested in more details of your business case and your vision on that.
Yes, indeed. So we're exploring different options. I mentioned that this is just one example, that transmission fees can be lower, but this is not yet in the regulation, and that's why I also said the regulation is a barrier. But that's why we're doing these pilots. Some of them are in virtual mode, so people are not paying according to layered energy system, but we're also running this in simulations with real data. And we're exploring in what way local energy can be made more favorable because it is using less of the grid, if you will. So there can be different ways to achieve it, and lowering the transmission fees would be one example. Exempting a tax, for example, would be another possibility. So we're exploring different ways, and we're trying to push the policy towards what is most favorable for all stakeholders. I agree that at this point we cannot just claim that transmission fees can be abolished for local trades, but these are concepts that we are exploring. And of course, if you would schedule a live demo, we can show you some results from our preliminary simulations comparing the layered energy system versus net metering now, net metering in 5 years, and in 10 years when it's phased out, and then you see the benefits in time. Very well.
Okay, thank you. Another question, not on the consumer's business case, but on your business case. If you open source your software platform, what will be the business case model of iLeco?
Correct, that's a good observation. That's on this slide. Indeed, so it's not the point that we open source the whole prosumer app. We're exploring different options with open sourcing the whole set of applications. This is our product, so it can be linked to any community deployed anywhere. So even if the other three applications are open sourced, we can link the prosumer app to those communities. Or we can also have a bare bones version of a prosumer app, so that a community can explore by themselves independently of iLeco with a bare bones interface that can show all relevant necessary information. But of course, it will not be powered by the advanced optimization software that we have. It's not going to have all the forecasting algorithms or gamification elements and so on. So we will open source the bare minimum version that is necessary to explore the LEF concept in a new community. And then once they see that they're willing to participate, then they can look for a prosumer app provider such as iLeco.
Okay, thank you. A question for clarification. Can an energy community provide flexibility services to the grid?
Yeah, so we have the flexibility rounds, which takes into account local but also external energy. So therefore, whenever flex is needed, a request is sent by the grid safety app to the community residents. Our software determines the flexibility potential and offers that flexibility. So whether it's needed locally or it's needed else in the grid, it doesn't matter. The layered energy system handles all three layers.
Okay, and does it also handle all kinds of flexibility markets?
Can you repeat? I cannot hear you well.
Sorry, and does it also open up access to all flexibility markets?
I wouldn't say all flexibility markets, but every community has its own flexibility. Yeah, you can see it as a mini flexibility market, every community by itself. Because if you imagine that this concept is deployed on multiple of those communities, and then multiple of these requests are sent, then multiple communities as a whole can help alleviate grid congestions. Yeah, we haven't explored in details the link with wholesale flexibility market here, but I don't see a reason why it wouldn't be possible.
Okay, thank you. Then there's a question on relation to the first draft of the electricity directive. Local energy community was a legal term in this first draft of the electricity directive. It was replaced by citizen energy communities. Do you claim any link with this concept?
Yeah, these are definitions of concepts. Yeah, so the whole point is that this is layered energy system is another concept that is deployed on a set of houses that are behind the same transformer, same minimum voltage transformer. So yeah, you can name it as a local energy community. You can also name it as a smart citizen community, because it's the citizens' participation that helps the grid. With our software, they're steered to use the system more, to use the system better. So you can also name it as a smart energy community as well, or renewable energy community. Or I think these are just terms that make concepts easy to talk about. But the point is that we have here a new system that is at the forefront of the energy transition, and we want to deploy it on sets of houses in different areas of different countries to explore the feasibility of this concept in helping the energy transition.
Okay, okay. In the first presentation today, we saw how steering and monitoring of devices is taking place. Can you tell us how you connect and automatically steer the assets of the members in the communities you are running?
Yes, yeah, that's indeed a valid question. So the Prosumer app, of course, has a front end that relies on a back end that relies on data. So we need to get data from the residents' homes, and we do this in different ways. We either install a gateway in that home, and then we communicate directly with that gateway that is attached, for example, to the smart meter or to the solar inverter or to the charging pole and so on. So a gateway device that we can communicate directly and get data from, or we partner with a third party that has those gateways and provides the data via an API, for example. We have used both cases in the past. So yeah, we need gateways, we need measurements of real devices in people's homes in order to enable this whole system to work. Of course, we can also link, just to mention that we, of course, a third way. So one is installing gateways, the other one is API connection, and the third way is if we could get, for example, P4 data directly from metering companies, then we don't actually need an actual device, but then we get the data directly from a metering company.
Okay, and can you say the devices you want to connect to, are they always ready for use and steering on flexibility, or does it need extra enhancements?
Well, it depends on devices. There are a huge number of devices, some that only, so gateways that only measure electricity. You have others that can also steer assets. For example, if we communicate directly with a battery inverter, for example, we can charge or discharge the battery, sending commands. So we do the full chain, as I mentioned in the beginning, but this is enabled through hardware, indeed. And there are different types of hardware. Therefore, we need to install the one that we need to read or control.
Okay, thanks. One last question. How is the price for the bids for the local day-ahead market and the flexibility market determined? What happens if there is no liquidity in the local market?
Yeah, that's why we have the 3 layers. So users can submit, local residents can submit market orders or limit orders. It's up to them to choose their preferences. If they're limit orders, then liquidity is lower. And then if nothing can be matched on the local market, let me see if this is, So if nothing can be matched on the local market first, then we go across local markets. where liquidity increases because you have multiple other communities. And then if that cannot be matched, then we go to the wholesale market where we assume sufficient volume is present to match all supply and demand requested by the local community. So this is in fact the role of the market service app, to check on all these three layers and match as much of the volume for the lowest price as possible.
Okay, I said last question, but one other question just entered my question window here, and I think it's very interesting. Who pays for the cost of the blockchain? Who are the miners, and how are they rewarded? And why is it cheaper than a central ledger managed by the DSO? It's not just one question, but please give one answer to this number of questions.
There are more questions. Well, it was a design decision that we don't want to have a lock-in effect, so that we entrust one party. So of course we have to pay a cost for that. But we're using, in this case, the Energy Web Foundation blockchain, which is a public permission blockchain. So anyone is free to write to the block, free to read the blockchain, and the permission set of nodes can write to the blockchain. So because anyone can use the blockchain, yeah, it is open. And indeed, there is a minimal cost involved with that. We've done a feasibility study on that. What would be the cost for transactions? The transactions needed by the layered energy system over 1 year, for example, and those were really negligible compared even to the electricity costs for a kilowatt hour. So costs are negligible to use the blockchain. The benefits are big, and of course there are costs because we want to pay the price for having this no lock-in effect, and that also because any party can provide a better software, a better app. They immediately have the blockchain available to link and to speak to the other apps, so they don't need to have any kind of onboarding, long onboarding process and developing APIs and so on. So yeah, there are trade-offs. There is no clear benefit of one over the other. It's a matter of design decisions and taking the best option that achieves those.
Yeah, and maybe can you say something about the cost right now for a consumer if you would join the layered energy system? Does he see blockchain annual bill?
No, the consumer is not going to see any blockchain costs. These costs are not passed on to the consumers. They can easily be handled by the parties running the different applications. So each party pays a small, so the costs are already negligible, and then they can be split across different apps, and therefore they're not passed on to end consumers. So they shouldn't worry about this. And also there are no mining costs or electricity usage because this particular Energy Web Foundation blockchain is proof of authority. So there is no heavy mining process happening like in Bitcoin, for example.
Okay. Well, thank you, Mike. Thanks for your presentation, and thanks for answering the several questions from the audience. And before going to the next presentation, maybe for the people who just joined, we are now in the middle of the 5th webinar from FLEXCON 2020. Currently, we have about 120 attendees in the webinar, and I would like to thank you already for asking a lot of questions using the question pane from the GoToWebinar. That really helps us to, well, get to a lively discussion with the speakers. And now I would like to introduce the third presentation. It's on hybrid renewable power plants, a cornerstone of the energy transition, by Philip Gladek from Spectral. Good morning, Philip. Well, Philip is a self-taught engineer with a background in business strategy. Coming from New York City, he came to the Netherlands in 2012 to help his sister start with Metabolic, a globally active sustainability consultancy firm. And in 2015, you started Spectral as a kind of a spin-off with a focus on really establishing and accelerating new initiatives in the energy transition and implementing smart energy technologies. So, Philip, please tell us why your hybrid generation is a cornerstone of the energy transition.
I'd be glad to do so. Thanks for the intro, Jan. I'm going to share my screen now. Can everyone see my screen? Or at least Jan, can you see the presentation?
Okay, Philip, please go ahead.
Great, thanks a lot. Let me just start my stopwatch here. All right, so yeah, as Jan introduced, I'll be telling you today a bit about Spectral's work in the domain of hybrid renewable power plants and virtual power plants, and giving some project examples, as well as walking you through some of the process we take in realizing these projects. Maybe a first short introduction about Spectral for those of you who don't know us. As Jan mentioned, we're a highly mission-driven organization that's focused on accelerating the energy transition, and we have a few key application areas that we focus on. The common thread there is the topic of smart energy control systems, and we have several solutions that are focused on energy efficiency and optimizing how different energy assets function, one of which is a smart building platform that's used to both analyze lots of data, but as well steer the heating, ventilation, and cooling equipment in buildings to deliver energy efficiency savings, but also flexibility services. Smart grids and also community microgrids are a big topic, and as well, as we heard in the previous presentation, supported by the emergence of new directives such as Article 16 from the Clean Energy Package. And I'll show you one example of one of our microgrid projects coming up. And hybrid renewable plants and virtual power plants are certainly one of the areas where we've been able to gain a lot of market traction, and we're proud to announce that Spectral is the de facto market leader in the Netherlands when it comes to this domain and controlling large-scale energy storage systems. To jump right into some project examples, so this case we started on in 2018 and was realized in the beginning of 2019. So it's the Hartel 2 hybrid renewable power plant. Here we have a 24 megawatt wind farm connected to a 10 megawatt hour battery system. I think to date still the largest energy storage wise battery in the Netherlands. In general, we have delivered for this project on behalf of the owner of the assets, in this case Green Choice, the mission critical control systems which enable to actually steer these two different clusters of assets as one integrated power plant. And we perform a number of key functions here, for example, managing peak power and import of power to minimize demand charges, but also, of course, providing ancillary services to the network to help balance the national and European network on behalf of the transmission system operator. And as well, smart forecasting and trading algorithms are deployed to optimize how the plant functions and to further optimize the revenue of the this combined power plant. A similar case that we have recently launched in July is actually the first mobile docking station in the Netherlands. So the battery containers you see there on the left are usually used as well for rental to construction events, but when they're not in use on offsite, they're brought to Gellehatsplein, where there's a wind farm of 12 megawatts, and they're integrated again similarly with the local wind turbines via our control systems. And here we had to make as well some special adaptations which actually allow for a hot swappable storage control. So basically, the logistics of all the rentals have to happen, and we need to be able to, while the system is actually operating, while it's delivering frequency balancing services, be able to unplug a container or plug one in when it's coming back, and our system auto detects and also auto scales the set points and the storage capacity in the configuration, so that without any break of or interruption in service delivery, we can easily add and take away containers. And we're currently working on another site at a large solar park with about 30 of these docking stations that will be used for the similar kind of use case. And in front of you, you see a render of the Rhino battery, which is going to be the most powerful battery in the Netherlands of 12 megawatts. Once it's realized, actually, our team is on site there now, and I'll be there tomorrow to do some final commissioning of the system. And we're going to be going live in about a week to week and a half with this site. And this particular project is also located in Lelystad on a private grid, which is going to be a very large-scale hybrid renewable power plant once it's fully realized. So in total, we will have about 220 megawatts of wind and solar at this location, as well as 36 megawatts of battery capacity. And that will be actually connected all behind the same high voltage connection to TenneT's transport grid. And within this project, similarly to other sites, we will be responsible also for managing the peak power of the combined plant, because the grid connection is only rated to 180 MVA, and peak power can reach, in theory, in the range of 250. So there we will be again 24/7 managing the power of the combined assets once they're realized. And one of the important topics in realizing these kind of projects, of course, is the planning phase, and not only looking at the business case, but also, for example, the technical dimensioning of systems. And so one of the questions we had, so obviously you need to be able to determine what size grid connection can you have optimally for the assets that you want to realize. And taking an example from one ongoing project, the question that I have for you today is, what percentage of solar energy do you think would be curtailed annually if you were to connect a 13 MVA PV plant and install this 13 MVA PV plant behind a 10 MVA grid connection? So the poll questions are listed there for you. I'm not sure where I'm actually supposed to see the poll answers, but
if you don't see them, Philip, I will tell them. Do you see them or not? I will. We have the votes are there. Thank you all. Most votes are on 1.02%, so in the middle. 31% votes for that, and then second is with 24% on 3.02% of curtailed energy, and both 0.14 and 6.55 are third on both 21% of the votes.
Okay, so a pretty even distribution. No one chose zero, I guess. So the actual answer there, and I'm not sure if you can still see my screen. Everyone can see my screen, I'm assuming.
Yes, we can.
Yes. So in fact, the answer was 0.14%. And what you see here on the graph is some analysis based on the plant in question that was conducted. So it's on the x-axis, it's a logarithmic scale, but you can see that basically there's only about 60 hours per year where production goes above the 10 megawatts, which is the rating of the grid capacity. And of course, the first step is to rate the grid connection based on your renewable plant. And after that, of course, if you want to add a large-scale storage installation, you need to be able to reconstruct and simulate the control behavior of that combined power plant. So what we often do is we actually build the optimization algorithms in advance in order to replicate some of the control functionalities of and the production output and the total load profile of the plant. And actually, in this case, we'll be putting about an 8.4 megawatt hour installation behind this solar plant, behind the same 10 MVA connection, and adding that extra 8.4 megawatts of battery capacity will actually only increase the curtailment by about 0.2%. So in total, we can have 13 megawatts of solar plus 8.4 megawatts of batteries and waste only about 0.3% of the total solar output of that plant. So this goes to show how essential it is to maximize the use of existing infrastructure at hybrid plants in order to help with the challenges that are currently in place with limited grid connection capacity and solving some of the key issues within the energy transition. And what does the project then look like? Well, in front of you, you see an example of one site where we have our control systems and active and standby systems and numerous layers of redundancy. Actually, what you can see here is that this is a very simplified version of the real setup. So in fact, there's numerous other sub-networks and a lot of other networking equipment in place, but it gives you a glimpse of that these kind of projects involve multiple layers of different control systems, both on the local asset level, on the microgrid level, and upstream to the cloud level, where we do a lot of the more process-heavy optimizations and forecasting. And so all of these systems need to communicate with each other in a highly secure manner in order to realize, these projects successfully and to realize the business case that was originally planned in advance. And this was a bit of a glimpse of the hardware. I'm going to show you a very fast demo of a simple customer-facing interface for one of the sites as a demo. So I can't show you everything because of some sensitive information, but I'll show you a glimpse of one of the demo accounts. So here you can see actually real-time data streaming in on the site level. You can see what's happening exactly with the wind and battery assets, the availability of the systems for up and downwards ramping. You can see then by function the set points being applied to the battery, the evolution of the state of charge, other information about its status, including also some external market data, which is used as part of forecasting activities. For all the projects we realized, we also have a 3D digital twin of the site that we build. So you can see actually in real time what's happening at this location. You can see the status of all the individual assets on a site level, or you can click, for example, on the wind farm and then see just the wind assets with some information about what's happening on the wind farm level. You can also click on an individual turbine and see information about that specific turbine, including various things like potential warnings or alarms. In this case, there's a communication issue, though it's non-critical as the asset is producing about 2 megawatts at the moment. The same goes for the battery systems. You can look at the site level or a specific container. And we do also track various statistics on performance for warranty compliance, as well as, our alerts engine sends notifications to the appropriate parties via various channels when there's issues with the hardware on site, which is the responsibility of the manufacturers. We also have some downloads and exports for reports, such as financial reports that show the asset owners exactly how much the plant is earning, broken down by function. So that's a quick glimpse of some of the software side of things. Moving back to the presentation. And it started from the start, so let me get to the right slide. So in general, I mentioned that utilizing infrastructure to its maximum by combining large-scale renewables and storage plants is quite a key aspect in order to enable an efficient energy transition. At the same time, you do have these physical limitations where when there's a lot of solar output at that site, then we don't have that much room if we need to also discharge the battery to help with, for example, balancing of the grid. That's why it's essential to combine these different plants together into a larger virtual power plant so that when one site has peak solar production and the other one, for example, has some room left because the wind isn't blowing, you can shift capacity between the assets, between the batteries, in order to provide still the same balancing service, but maximize the use of infrastructure. And going further beyond just the hybrid renewable plants, it's important to also put other types of flexibility, such as demand-side flexibility, in the mix. And as well, with the emergence of smart grids and microgrids, this becomes a lot more feasible. So in general, we have a number of projects where we're also combining these kind of microgrids, which also have their own local production, as well as things like heat pumps and EV charging points, batteries, and bundling them together into a pool with these large-scale hybrid renewable plants. So one of the sites coming up, to give an example, Republica in Amsterdam is one of the microgrids where we also have a legal exemption from the RVO to develop a private net on behalf of the future community that's going to live there. So in total, we have about 20,000 square meters of new build, large hotel, several apartment buildings, cafes, offices, so a little village on a plot. And underneath it all is a basement and a parking structure with about 100 parking spots, 50 of which will have smart EV charging points. All of those will be connected to our microgrid optimization system, including also the large-scale battery of about 1 megawatt that will be inside of its own special room, a battery bunker inside of the basement. Next to also the big heat pumps, and we also have thermal storage there connected to an aquifer thermal energy storage system, including also above ground thermal buffers. And all of these assets will be connected to our microgrid platform. And using the flex of these different assets, we can more optimally deliver a range of different services, both to ensure that locally peak demand is managed and that the distribution network isn't put under too much strain, while at the same time being able to deliver balancing services to the transmission system operator using this pool of flexibility and being able to ramp up and down assets depending on the needs of the site. So that's a quick overview of some of our ongoing work in this domain. And now we can switch to the questions.
Well, thank you, Philip, for this presentation and giving a hybrid a new meaning for me. So good to hear that. And we have some questions from the audience. I start with the first one. If parts of a virtual network are not located at the same place, for example, the Hartel wind farm and the mega battery would not be at the same location, how does the operation of the virtual power plant change? And what would the cost be for internal transmission in the virtual network?
Yeah, good question. So if they were separated and not behind the same grid connection, well, then obviously, the whole grid demand charge structure would be different, and we wouldn't be steering the assets in the same way, taking into account those local constraints of the single connection. Then we would have two connections we would have to try and manage, and especially important for the battery system, because what we normally do is, in the Netherlands, you don't pay for feed-in energy the same way that you pay for demand side import and peaks on your import side. So we always try and optimize when we charge the battery when there's actually wind available, so that we don't actually import anything from the grid, and that saves quite a lot of money on an annual basis. Now, if you don't have that ability to hide your battery charging behind another profile of, for example, a wind farm, that would incur a lot of extra costs for the asset owners. And also, the optimization would be inherently different because you wouldn't have that single point of coupling as a constraint. So I hope that answers your question.
Yes, I think so. I hope also for the audience. A second one, how to avoid the wasting of 0.14% of the energy paid for the cost of the battery?
Well, to be clear, the 0.14% was what you would waste just by putting the PV plant behind a 10 MVA connection without any battery. So obviously there's a cost optimum as well when you're planning your site. You know, if you go above 10 MVA and to a 13 MVA connection, that extra cost you would have to pay is often not worth the 0.14% of the energy that you lose out on. But when you add the battery, there are of course ways you can try and minimize the waste or curtailment of solar by forecasting the production of the solar and then trying to, as much as possible, schedule your battery to charge when there's excess or peak solar production expected. So it is possible to do that, and we do in fact do that in our projects. But what you see is if you want to optimally use your assets to provide multiple services and help also balancing the national network, there will be there is an optimum where you know, to utilize the infrastructure in the best way. That simply means you will waste that top bit of, you know, in this case with the battery involved, around 0.3% of the total plant production, which is not a huge amount.
All right, thanks. You showed us the level of curtailment. The question is, if there is such a low level of curtailment, how can you recuperate the additional cost for the battery with the hybrid solar park?
I guess I think the question is asking more why is there such little curtailment? Because, well, for one, especially when you're delivering frequency containment reserves, so FCR, known as the primary reserve market as well. If you look at actually the power levels that you typically deliver, let's say for an 8.4 megawatt battery system, you're usually sitting within, so almost all the time you're delivering plus or minus 10% of your rated capacity, which is in this case, you know, below 1 megawatt. So actually, in effect, when you look at the coincidence of peak solar production, well, half the time you're already charging your battery when delivering FCR during those peaks. And the other half the time or less, you do have to discharge and curtail a bit. Of course, there are tricks of minimizing that. And also, you know, again, when we want to do other, let's say, wholesale market services, we always try and plan those in an optimal way to not curtail the solar. So it is a very complex optimization that uses numerous forecasts and is constantly updated on a rolling time horizon. But there are certainly, leveraging AI-based techniques and traditional control systems methods, you can minimize that waste while still earning the revenues you expect on your battery system.
Okay, that clarifies. A more technical question: do you connect the battery directly on DC or after the AC invert? So far in all the projects that we were looking at, they're all AC coupled, mainly also because the market is not really geared towards DC integrated plants. All of these systems, all the big manufacturers offer their solution standard with an AC inverter connected, and sometimes that's strange voltage levels or non-standard voltage levels, but it's typically always AC. Okay, do you expect that to change in the future? Or some developments there?
Yeah, I do think there is in general, of course, a trend towards doing more with DC. I do think there will be more equipment, more power electronics hardware on the market that's DC ready. So you can, for example, couple your PV directly to the battery on the DC bus. Although I do have my doubts as to how much that will take off, mainly also because on one hand, you have, the PV inverter market is also quite mature and all geared towards AC coupling. If you evaluate the difference, the efficiency gains that you gain, you know, the newest transformerless AC inverters operate at a, you know, around a 97% peak efficiency, and on the DC side you might get 98% or so. So there, I mean, there's a very limited difference in the end of you know, efficiency gains in that respect. If you of course can connect devices that currently use inefficient DC or AC to DC converters, like you know, your typical laptop charger might operate at an 80% efficiency, or in general there's other wins you can gain through DC, but it does come with a lot of complexity, and mainly because the market just isn't ready and doesn't have the experience to work with DC more broadly.
Okay. Well, I have one last question, Philip. Just have to look carefully. How can we use the extra peak at moments that there is no capacity issue at all? And how much then on the 0.14% would you win by that?
I'm not sure if I understand the question exactly. How would we use the peak of the solar production, or can you maybe repeat that one?
Well, it's if there would be a possibility that in the grid there's no limitation, so you could have an extra peak where you know there is no capacity issue. Could that be useful, and could that help to overcome the 0.14%?
Yeah, well, I mean, in general, in this case, the main constraint is that you have a physical substation and cables that are all dimensioned towards that 10 megawatts. So, you know, in general, you can, of course, push it a bit, because most fusing protection has trip curves that allow for going a bit above that 10 MVA rated capacity. But in general, yeah, it's not something we typically do, and you certainly don't want to trip circuit breakers on a 10 megavolt connection, because yeah, then you have to call Jan and Steden, and they have to come down and fix the issue, and it's not going to be a good story. So I don't know if I fully answered the question, but yeah, that's as far as I interpreted what it was about.
No, I think that what you say is clear, that you are already on the limit of your capacity connection. So there's no reason you to going above that.
For example, like at the Rhino site, we actually get measurements not only of the real power and current flowing over the cables, but also actually temperature. And so you can, by having some also consideration of temperature, push again a bit the 10 MVA limit and see whether or not, you know, you have that extra space you can play with. But in general, you know, peak solar production days typically happen when you have like you know, a long consistent profile, and you know, that means that probably yeah, well, in the Netherlands there's often clouds, so there can be intermittency, but if you have a fixed feed-in you know, above that, then your cables are going to run hot pretty fast. It's not like when you have volatile short spikes where you can go a bit above the 10 MVA. Okay.
Well, thank you, Philip, for both your presentation and going into discussion with the audience. We are going to the last presentation of today, and that will be about investment plans for grid and infra by Wurth from Siemens. Tom is a strategic energy transition consultant at the Siemens Smart Infrastructure department. He's experienced in investment planning within chemical industry and energy infrastructure business. He was responsible at Steden for some years for the strategic grid planning, and last years he's involved in the development of an approach to develop robust energy infrastructure plans within the context of a deep and certain future. Well, Tom, after 3 presentations, I think you can help us on how we can still do a reliable planning for the future. So please start your talk.
Thank you, Jan, for your...
Can you put on your webcam?
Yes, my webcam is on. Can you hear me, by the way?
Yeah, we can hear you quite well, but I cannot see you.
Oh, yes. Haha. And now, can you see me?
Yeah, great, Tom. Okay. Success.
Okay, we're set. So thank you, Jan, again for your introduction. Ladies and gentlemen, how can we create robust adaptive investment plans for energy infrastructure given the deep uncertainty of the energy transition? This question is central to the Gridmaster initiative that I will address in the coming 15 minutes. The presentation is divided in 4 sections. I will start with the context of the Gridmaster initiative. Then I will dwell on what we mean by an adaptive investment plan. After that, I will give a short outline of the Gridmaster initiative, and I finalize the presentation with the modeling approach that is the foundation of the development of adaptive grid planning within the Gridmaster initiative. So let me start with the context. Grid operators are responsible for a safe and reliable energy transport. And in order to safeguard sufficient transport capacity, timely planning of grid expansion investment is necessary. For example, in the Port of Rotterdam area, grid operators have to deal with a lot of potential future developments, like offshore wind landing capacity increase in the port area or the phasing out of certain refineries. Also, the development of flexible energy solutions like power to hydrogen, demand-side management, and battery storage are developments that are relevant for the grid planners to consider. These future developments have one thing in common. It is uncertain whether they will happen or not. And these uncertainties in the energy transition have impact on the energy infrastructure capacity requirements. Putting the various developments in a timeline from 2020 till 2050, scenarios of transition pathways are developed that could happen in the future. This picture looks already quite complicated. However, in real life, the potential scenarios that could arise are numerous, maybe millions. And this is very challenging for grid planners of energy infrastructure, because they actually need to answer this question: which investments in energy infrastructure will be needed to facilitate transition pathways? The impact of making wrong decisions is quite high, because this can lead to stranded assets. It can lead to insufficient transport capacity for actually valuable transition pathways, and can also facilitate suboptimal value chains. So making the right decisions is thus of paramount importance. To cope with deep uncertainties, it is necessary to create an infrastructure planning that is adaptive. That sounds nice, but what is an adaptive investment plan? An adaptive investment plan is robust. That means that the performance of the plan is acceptable in many futures. This is realized by the definition of no-regret investments and flexible investments. No-regret investments are investments that are effective in many futures or scenarios, and those investments can be planned immediately. Flexible investments, in contrast, are investments that are effective in specific futures. In case these specific futures emerge, these flexible investments should be planned to adapt the available transport capacity to the needs of the evolving energy system. So currently there is a need for a grid planning method that results in an adaptive investment plan given the deep uncertainties of the energy transition. And a promising modeling method for this is based on the explore and adapt paradigm. In this modeling method, investment plans are stress tested in a multitude of scenarios, and this modeling method is inspired by the Delta program. The Delta program is a program in the Netherlands to safeguard basically the Netherlands for water safety threats to guarantee water safety, fresh water supply, and spatial design in 2050. And this long-term goal is threatened by uncertain changes like rising sea level or more rain. And basically by applying a modeling approach of searching or exploring an adaptation, an adaptive delta management policy is designed. And this problem, the delta program is addressing, is really similar to the energy infrastructure development challenge that we would like to address in the Gridmaster project. The objective here is to create long-term value for a geographic area. And this is affected by factors like growth of renewable-based mobility and the evolution towards a circular plastic value chain, to name a few of the factors that impact the energy transition. By structurally exploring the energy transition pathways for a geographic area, adaptive investment plans for energy infrastructure could be identified analog to the way adaptive investment plans are identified for the Delta program. Now I would like to share a fictive example of an adaptive investment plan for hydrogen infrastructure in the Port of Rotterdam to make it more concrete. Depending on the actual transition evolution, the requirements for hydrogen infrastructure will change. The current hydrogen infrastructure in this example will be a bottleneck from 2021 onwards in certain futures. If from that moment in time, no additional investment measures are taken, the hydrogen infrastructure cannot accommodate all potential futures. To prevent this, it's possible to invest in a new 40 gigawatt or a new 20 gigawatt pipeline, or to invest in making available 4 gigawatt transport capacity by reusing of an existing natural gas pipeline. All futures can be facilitated in case a 40 gigawatt new pipeline is planned. All futures till 2035 can be facilitated in case the 20 gigawatt new pipeline is planned, and all futures till 2027 can be facilitated in case the reuse of the existing natural gas pipeline is opted for. From these investment building blocks, various investment routes in the future can be constructed. An example of such a route is to start with the investment, reuse of the natural gas pipeline. Potentially, this investment turns out to be insufficient to support future transition pathways. In case that becomes clear, it can be decided to invest in the 20 gigawatt pipeline or the 40 gigawatt pipeline at that moment in time. In case the 20 gigawatt pipeline is chosen, there is a chance that later in time, still additional investments are needed. These various investment rounds into the future can be compared with one another on criteria such as the capability to support energy transition scenarios and the infrastructure investment cost. From this evaluation, the most attractive route can be chosen as adaptive investment plan. And hopefully it's now clear to you what an adaptive investment plan is, and also that it's clear that there should that the methodology to develop those plans is needed. And it's time now for a poll question. And Adrian, I'm interested in the opinion of the audience. Can you show the poll, please? And the question there is, who should develop the methodology for an adaptive investment plan for energy infrastructure? And you can read the answers for yourself. I cannot see the scores myself, so Jan, if the results are available, I'm happy to hear them.
Yes, I will let you know, Tom. Just a second.
Thank you.
Okay, the results are there, and well, there's a clear winning option, and that's the fifth one. Collaboration of at least the above mentioned parties scores 55% of all votes, with grid operators on a second place with 20%. So I think quite a clear vision from the audience on who should develop the methodology.
Thank you. So that's really actually in line with how Siemens and also the partners that are involved in the Gridmaster initiative think who should be involved in the development of the methodology. Because the required knowledge for the development of an adequate methodology is such broad and deep that we think it's impossible for a single organization to be successful in this development. So the audience and actually, we are aligned, or myself are aligned. That's nice. And that brings me to the Gridmaster initiative itself. The initiative is aimed at the methodology development of adaptive investment plans of energy infrastructure, as already told. And it started in 2019 with a proof of concept that we called Windmaster. And coming month, we hope to start with the second project that we call Gridmaster HIC Rotterdam. And HIC stands for the Harbor Industrial Cluster in the Port of Rotterdam. That will be a project that lasts for 10 months. And in the meantime, the partners within the Gridmaster HIC Rotterdam project are aiming to develop further spin-off projects. So the Gridmaster HIC Rotterdam project will be executed by 11 organizations: the grid operators TenneT, GasUnie, Stedin, the Port of Rotterdam, the Province of South Holland, the Municipality of Rotterdam, Smartport, TNO, Delft University of Technology, Quintel, and Siemens. And to give you more insight into the work that will be executed in the Gridmaster HIC Rotterdam project, I will conclude this presentation to share the base of the modeling method that will be further developed in the project. First of all, we are aiming to develop a decision support tool that helps identify adaptive plans that perform acceptably well in a multitude of futures. And to structure this decision problem, we use the XLRM framework. Here, X indicates the external factors that decision makers cannot influence. The L indicates the policy levers that represent the factors that can be controlled by the decision maker. R forms the relations between the inputs X and L and the outputs of interest for the decision maker. R actually is the simulation model that models the dynamics of the considered energy system. And finally, M stands for the metrics that will be used to determine the success of a policy option that is stress tested. Application of this framework to the adaptive investment grid planning problem leads to the following structuring. So here, the X are the relevant external factors influencing transport capacity needs. And those factors can be divided into factors that that basically lead to structural change in the energy system, like the phasing out of a refinery, for example, and factors that are influencing the potential operation of the energy system, like a market design or the wind speed. And the flexibility assets and dynamic operations are part of the relevant external factors to be considered. So L are the investment plans of energy infrastructure that can be controlled by the grid operators, and those plans are stress tested. The R, that's the simulation model. We are planning to develop a multi-model simulating capacity bottlenecks and corresponding investments of energy infrastructure. And finally, the metrics are robustness metrics that say something about the available transport capacity and also the level of infrastructure investments. Based on the problem framing via the XLRM method, a multi-model will be created that will be used as a simulation model. So elements within this multi-model are the investment plan model, an investment behavior model, a market model, various technical network models or load flow models, and potentially in the future also other models like flexibility models. A core element of the multi-model is the exploratory scenario generation model. In this model, in a structured way, scenarios of energy transition path can be generated. In traditional scenario creation, in a qualitative way, narratives are constructed that are subsequently translated into quantitative scenarios. These form the base for strategic grid planning. In contrast, the exploratory scenario generation model, all factors that affect energy transition pathways are combined in a structured way. By doing this, a scenario space is created from which the main transition pathways can be derived. This results in a more elaborate insight in potential energy transition pathways. And by using this more elaborate insight in the strategic grid planning process, the effectiveness of the adaptive investment plans for energy infrastructure will increase. The chance of future unexpected developments that has not been accounted for in energy infrastructure planning is lowered. The multi-model that we are developing is subsequently applied in a process in which investment plans are stress tested in multiple futures. Many computational simulations will be conducted per investment plan where the scenario in the scenario space is varied. In this way, the robustness of an investment plan can be tested and promising candidate investment plans will surface. Also, it's possible to conduct vulnerability analysis to identify in which futures investment plans fail. Based on this analysis, investment plans can be redesigned in order to improve the overall robustness of candidate investment plans. This process will be iterated in order to improve the robustness of candidate investment plans, and hereafter, the most promising adaptive investment plans will be visualized to obtain decision support information for decision makers. So, ladies and gentlemen, we have arrived at the end of the presentation. Now, I'd like to summarize by repeating the key points of the presentation. First of all, the deep uncertainty of the energy transition calls for adaptive investment plans for energy infrastructure. And notice that flexibility options are part of the deep uncertainties that grid planners should consider. The second key point is that in the Grid Master Initiative, the methodology for adaptive investment plans for energy infrastructure is developed. And the foundation for methodology development is stress testing of candidate investment plans in many scenarios. And an expected next step is the Grid Master HIC Rotterdam project. So thank you for your attention, and I'm happy to answer your questions.
Michael, thank you very much for this interesting presentation. In some way, it makes me think of a car navigation system that is planning for roads and on roads that still have to be built. So, yeah, really interesting, and I think a necessary tool for the future, surely for us as grid operators. We have a few questions. The first one, you are talking about uncertainty in the future. All the uncertainty you are talking about is the expected uncertainty you are thinking of. What about the unexpected uncertainty you can think of right now? For example, a black swan event, a corona pandemic. So how do you think about that?
Yeah, so for now, a corona pandemic, I think we as a community are aware that that can happen. So that's not a black swan anymore, but of course there could be black swans that we cannot imagine now. It's really hard to consider that as an uncertainty, but actually by I think in the scenario space that we are building, because that is very elaborate, when there pops up a black swan, then it's quite easy to implement that black swan that isn't a black swan at that moment in time. But it is really hard to plan for the really unknown. So if there's an event or a factor that in the future will have a big impact and we couldn't imagine that now. Hopefully that answers the question.
Well, thank you. It answers how you now see that problem. And I understand you see the problem, but it's quite difficult to model something you don't know. So that's clear. A second question, how much automation is involved in the modeling approach, and what steps involve necessary human input?
So how much automation? Basically we are planning to build a multi-model, and that comprises of several models. These models will be linked to each other in a software infrastructure, and so actually during the simulation, a routine will be initiated, basically to call the various submodels in the right order, basically to have a good simulation model. And we, during this actually analyzing phase, we are using all kind of analytics, and algorithms, basically to search the scenario space, and also search the vulnerabilities in investment plans. So there will be quite a lot of modeling and automation.
And is there, for example, I saw some of the outcomes, is there, for example, the possibility, which can be seen as human input, to say, okay, we see a route from A to C going via B, but I would like it to test it to go via D. Those kinds of variations, can you put them in manually?
Yes. So it's really interaction, so human interaction with the multimodal. So basically, during the process of stress testing, the computer basically analyzes a lot of simulation results, and humans, or we, should interpret those results. And basically, on our interpretation, we can also identify weaknesses of potential investment plans. And basically, by understanding those weaknesses, we can redesign a potential adaptive investment plan. And that improved investment plan should be stress tested again, basically. So there's a constant, I would say, interaction between the computer and the human beings, basically, or the humans.
We still have a role.
Yes, it's very important.
Good to hear, and thank you, Tom, for your presentation and answering the questions. And with that, we've come to an end of the 5th webinar from FLEXCON 2020. First, I would like to thank all presenters of today: Pieter, Guillaume, Mike, Philip, Tom. Thank you for your very interesting and clear presentation. Secondly, behind the GoToWebinar screens, people are making this possible. Alicia, Michael, Elia, thank you very much for your contribution and making it working again in a great way. And then the audience, we got a lot of questions. I hope you enjoyed this webinar, and I also have to mention that you will be able to find all presentations and the recording of this session and the previous sessions on the FLEXCON 2020 website. It's a great way to, well, even further share the interesting insights of all these presentations. Next week, we have the last and 6th webinar from FLEXCON 2020. It will be on active managed buildings. I hope to see you all by then. Have a nice day. Thank you.